8.4 is all about annuities, calculating of annuities. An annuity, as our book tells us, is an interest-bearing account in which we make a series of payments of the same size. And if one payment is made at the end of every compounding period, the annuity is called an ordinary annuity. The future value of the annuity is the amount in the account, including interest, after all the payments have been made. So we've seen this A before, right? If you remember, we saw A equals P times 1 plus R over N to the Tn, and we use that for compounding of interest. This is very similar to that. You can see that that same part appears on our screen here, 1 plus R over N to the Tn. The difference is we don't have a P anymore in here. We're not starting with a single amount because we're making regular payments in. That's what our R value is going to be, big R value anyway. And this is going to help us calculate what's that future value, what's in the account at the end. And what's in the account at the end minus all the payments we have made is the interest. All right. So again, A is the future value or the end value. What are we trying to strive for? Big R is the monthly payments. What is our monthly payment that we're making in? R is the interest rate as a decimal. T is time in years. N is the number of compounds in 1 year. We've seen that. And finally, 1 is 1, i.e. greater than 0, less than 2. You know, the value of 1 itself. I was trying to be cheeky here with this 1, and then it occurred to me that defining 1 is kind of hard in that what is 1, right? I guess it's greater than 0 and less than 2, but that's really what 1 is. But this equation is the key to 8.4. We're going to look at this equation several different ways in 8.4 to solve the problems, but this is the equation. Again, let me caution you. This equation does appear on page 420 of your book. However, their version of it and my version of it are slightly different. They use an M value, which I find to be very strange because M essentially is R divided by N. So why would you not have that in the problem? Why would you want to calculate that separately to make your equation look nice? I don't understand it. So this is the best way to calculate this because once we put the elements in, our calculator can do all the work and we don't have to do anything else. We don't have to do any other calculations that we have to feed into it. So that's one of the advantage of using my equation versus the books. All right, so let's go ahead and make this a little bit smaller and let's look at example 1 on page 420. Suppose that Christian has a daily habit of buying tall cafe lattes that cost $1.95 at Starbucks 6 days a week. If instead he puts this money into an ordinary annuity, how much would he have in his account if he deposits his monthly savings in the annuity for 15 years? And assume that the annual rate paid on the annuity is 3%. Again, it never hurts to start these problems by putting in everything that you know. In our case, we're trying to figure out what the A value is. So the A is the unknown piece here. The R is his monthly payments that he's putting in, big R anyway. Now, they don't give us the monthly payments that he's putting in there, but they do know that he's going to start saving $1.95 every day. So to calculate our R, we're going to take $1.95 times 6 times 4. Times 6 because he did it 6 days a week, and times 4 because he's doing it once a month, and every month has 4 weeks. Let's bring up our calculator. Clear off any old results. 1.95 times 6 times 4 is going to give us $46.80. So it looks like his monthly trip to the bank or electronic deposit or whatever he's doing to get the money into the annuity is going to be $46.80. All right. So big R, $46.80. Little r, the interest rate, looks like he's getting 3%, it said. And so again, for us, that's going to be 0.03. We always want the decimal equivalent when it comes to interest rate. All right. The time involved here. He's going to do it for 15 years. Wow, that's kind of a long time to do that. Great. The number of compounds. So he's doing it monthly. And so we're going to say that's going to be 12. So now we can set it up so that our calculator can do the brunt work here. All right. A equals. We have our big R value, 4680, times, sub parenthesis here, 1 plus r, so that's going to be 0.03 divided by n, 12. This sub parenthesis gets taken to the power of 15 times 12. Then the whole thing is minus 1 to it. And then the whole thing here is divided by 0.03 divided by 12 again. Close that 0. And then we close the parenthesis here. And now it's time for our calculator to do the brunt work. So let's bring up our calculator and I will show you exactly how to do this. Step by step. Let's move it over here so we can see our amounts at the same time. Let's go ahead and clear this 4680 anyway, because what we're going to start with is inside the parentheses. And in fact, even though there's one giant parenthesis, we're going to start in the sub parentheses. And we're going to start right here as in 0.03 divided by 12. So we say 0.03 divided by 12. And we say enter equals whatever we want to do. Get that number. Then we say plus 1, because as you can see, there's a plus 1 here. So we're going to say plus 1, enter. Always entering on this one. All right, so now we have this inner parenthesis here. We have the amount, but now we need to take this amount to the power thereof. So on our calculator, there's a great button right below the clear, the little caret button. We're going to hit that, and it's going to say, what power do you want? I'm going to say 15 times 12. And you'll notice how my 15 times 12 stayed into the exponent of this ands. And again, ands is always the last number that we see here. And again, I'm going to hit enter, because now I know what this entire parenthesis is with the exponents. Then we say minus 1. Enter. Okay, now we know what the top of our fraction is inside of the big parenthesis. Now we divide, because there's a divided by sign. We want to divide by this part here, so we want to use a parenthesis for this, because we want to make sure that we divide by 0.03 divided by 12. If you don't do it that way, then the calculator is going to have a problem, because what it's going to do is it's going to take 0.567, it's going to divide it by 0.03, and then it's going to take that amount and divide it by 12, which is not the same thing as taking 0.567 and then dividing it by the total of 0.03 divided by 12. So these parentheses are utterly critical to the process. But once those are in there, hit enter again. And now we've got the entire parenthesis taken care of. So the last thing that's required in this problem is to say times 4680. And so we'll say times 46.80. And the answer is $10,622.38. So let's write that onto our screen so we have it. $10,622.32. All right, that was quite a bit of money. So in our account, now how much in interest did he get? Sometimes you'll get this question as a part of this. Because remember that the A, this amount, this $10,622.38, includes all of his money that he put in the account, plus the interest. So remember, he made payments of $46.80 every month, so 12 times a year for 15 years. So essentially, to find what he put in the account, we're going to take 4680 times 15 times 12. Let's bring our calculator back in here. Let's clear this amount. I'll say 4680 times 15 times 12. Looks like he put in $8,424. That's kind of a big amount. So then if we take 8,424 and we subtract it from the 10,622.32, we'll know how much in interest he made in this annuity. Again, sometimes this comes up, which is why we're doing it on this example, even though it didn't ask for it. So we take 10,622.32 and we subtract the 8424, and we can say his interest was $2,198.32. Let's translate that back to the screen so we have it. Again, give it context, give it that dollar sign, $2,198.32. So we made a pretty decent amount of interest over 15 years. Nothing to scoff at so far. Definitely, hopefully, worth the price of giving up that latte 6 days a week.